Recording in progress.
Let's start. Our today's speaker is Kirill Snishko, who was graduating from Taras Shevchenko University in Kiev in 2010. Then he did PhD at Lancaster University, and then he did some postdocs at Weizmann and in Karlsruhe, and now he has a permanent position at CA Grenoble, I think so. And he will talk us about something that's written here, and please go.
Thank you. Thanks for the introduction and thanks for inviting me here. What I'd like to tell you about today is something about quantum computations, about how well they work, what should we expect from them, will they change our lives anytime soon or maybe not so soon. But before I go to that, I'd like to introduce you Grenoble a little bit, because it happens to be a nice place and not too well known, but it's worth to be known. Then I'll give a big overview on the status of quantum computing. And then I'll tell about a project on benchmarking quantum computers in which I'm involved and a particular case study. So Grenoble. Grenoble is not far from here, actually. That's the city in France. We're here. And if you zoom in on the city, you realize that there is a whole area called Scientific Polygon. Huge campus with lots of researchers. From what I hear, it's the second biggest research center in France. In reality, it looks like this. One river, another river, and between them a huge peninsula, most of which is research centers. This is the CEA. This is where I work. This smaller campus is the CNRS, the French Academy of Sciences. This is Institut Laouel-Langevin. It has a synchrotron. There are big magnets there. There was a record-breaking MRT recently done there, if you've seen on the news. To me, as a condensed matter physicist in origin, it was very interesting to learn that actually quantum Hall effect was discovered there. Klaus von Klitzing came to Grenoble to measure his sample in big magnetic fields. And if you read his affiliation here, it's High Field Laboratory of Max Planck Society, Grenoble, France. That's what I would call European collaboration, and never mind that the European Union was established 12 years later. That kind of shows that the European community is not a static thing, it's evolving. One of the recent examples of evolving is Ukraine being granted a candidacy for the EU, and being a Ukrainian, I hold European collaboration close to my heart. Now, having told you about my political beliefs, I can tell about my beliefs on quantum computing. Now, why do we want quantum computing? Why at all bother? Why does everyone talk about it? Well, the reason is that it promises some computational advantage. Not everywhere, but in some problems. For example, if you want to factorize integer numbers, there is Shor's algorithm that promises exponential advantage. And since our encryption is largely based on that, one can break encryption. In fact, one can break many other encryption systems based on a similar algorithm using quantum computers, gaining an exponential advantage. In principle, if it works. There is Grover search, which only offers polynomial advantage. There are algorithms for solving linear systems of linear equations, which offers also exponential advantage, but with some caveats. Again, I'm a condensed matter physicist, so for me, what's interesting is quantum simulation, and the exponential advantage there, it could come from the fact that the Hilbert space of a system is exponentially large, it's costly to calculate the wave function on a computer. It's exponentially big quantity of numbers, but on a quantum computer, it's natural environment to model. If you want to know more about these algorithms, I recommend you this review, which is not mine. I've realized I forgot to put the name of the author here. It's a beautiful review with different algorithms and their variations and their potential applications. That's why we want quantum computing. Now, how do we want quantum computing? How do we build a quantum computer? And in fact, if you go to Wikipedia, that's a table, in fact, about half the table on different architectures for quantum computers. There are various ones, photon polarizations, quantum dots. Arguably, the most advanced one so far is based on superconducting Josephson junctions. For example, IBM, it has the roadmap for scaling up these superconducting quantum computers. This is an old roadmap. In 2023, they aim to present a computer with 1,000 qubits and another one with a better architecture, but only 100 qubits. And they did present both of them, and they keep scaling up. So one could think that quantum computers are already a reality. They are big. They are soon going to address real world problems. There is a subtlety here, however. They are big, and scaling them up is a challenge. That's what IBM is doing. But there is also the issue of quality of the qubits. And to illustrate that, let me use an example related to prime factorization. Prime factorization, as many other quantum algorithms, it requires running a classical subcircuit. You want to factorize integer numbers. Part of the algorithm involves multiplying integer numbers, which is a classical operation. And there are theorems, mathematical theorems, that a quantum computer can, in principle, do any classical algorithm. So in principle, executing pieces of classical code on a quantum computer and doing that in a state of superposition, no problem at all. In principle, but in reality, they are not reliably executable. There are too many errors. What do I mean? How do we see that? So I want to multiply two integer numbers. What should I do? I should multiply the first bit with the first bit of the second number, the first bit with the second number, second bit with the first, second with the second. So I should multiply every bit with every bit. Then I should do some addition on top, but let's forget about that. So if I want to multiply two 64-bit integers, something easily doable by my laptop or your phones, one should use 4,000 bit-by-bit multiplications, which is an AND logical operation. How does one implement an AND logical operation in a quantum computer? It's called a Toffoli gate. If this is 1 and this is 1, it flips the state of the third qubit. But modern quantum computers, they don't have 3-qubit gates. They have 2-qubit gates. So to implement a single AND, you need 6 2-qubit gates and a bunch of single qubit gates. I'm going to forget about single qubit gates because they are reasonably accurate. The error typically comes from 2-qubit gates. And they are also incredibly accurate. The gates are executable to accuracy up to 99.9% on superconducting quantum computers. So incredible accuracy. Although if you think about it, it means 1 in 1,000 gates makes an error. And if I have 6 of them, then the probability of making an error in this logical AND operation is already 0.6%, 6 times larger. So that's not the end of the story, because we need 4,000 those AND operations. And if we say that we want to multiply and everything is correct, no error has happened, the probability of getting correct multiplication is 10 to minus 11. You basically never multiply 2 reasonable integers correctly on a quantum computer. And even if I'm generous and I say, suppose the end accuracy is not 99.4%, suppose it's 99.999%, then the probability of correct multiplication is 96%. Already not bad. Most of my multiplications are correct, but still, it means that 1 in 25 multiplications makes an error. If your numerical simulations made an error in 1 in 25 arithmetic operations, you wouldn't be happy about that. Which means that for good use of quantum computers, one really needs to improve the quality of the hardware by many orders of magnitude, which is challenging, because even gaining 1 order of magnitude is a lot of work. How does one improve many orders of magnitude? Turns out that people have thought about this. There is a field called quantum error correction. It is possible to encode a single qubit in many qubits. You cannot copy quantum information. No cloning theorem forbids that. But you can distribute it in a clever way, and using this redundancy in distribution, you can later recover the information in your original qubit and correct for some errors. There are different ways of doing that. The oldest one is the Shor's code. The most popular so far is the toric code. People say that color codes are even better. There are many ways. Conceptually, everything is there. Basically, they say that depending on the code, you will have some threshold. And if the probability of the error, P, is smaller than P threshold, as you encode your information in more and more physical qubits, the error probability on this big logical qubit is going to scale down exponentially as you increase the number of physical qubits. So if you're below threshold, you add a few more qubits and you get an order of magnitude. A few more, another order of magnitude. Conceptually, everything's there to get many orders of magnitude. For the toric code, typically it's 1/2, because there are 2 types of error. If you see here, you see it looks like a structure here and an identical structure here. Because there are 2 types of error. You can have a bit flip error when there is an error in the logical value, and you can have a phase flip error when there is an error in the phase between 0 and 1. So the Shor's code, it uses some number of qubits to correct for bit flip errors and some number of increased these blocks to correct for phase flip errors. So you want to correct for 2 types of errors. You have n qubits. You have, or on the toric code as well, you have a rectangle, you have a square. Square root of the total number of qubits is the actual number that matters. So A is typically 1/2. It's not too small. The main problem is really getting below the threshold, as I will show in a moment. Because Google basically tried doing that. And they published a paper 2 years ago that they can increase a surface code. A surface code is more or less the same thing as the toric code on the previous slide. So they said, we use a 3x3 code and we use a 5x5 code, and the 5x5 code works better. That's the decay curve of the quantum information, and per 1 cycle of error correction in 3x3 you lose 3%, and in 5x5 you lose just a bit less than 3%. So you could think, okay, now we can start scaling up. But if you read in detail and think about it, you see that 3% is much larger than 0.1% C0 error. So this encoded system, just by being there, it creates more error than it corrects. And if you read carefully, what they say towards the end of the article is that this is a finite size effect. If you kept increasing, then bigger systems would be worse. They're not yet below threshold. And to be below threshold, one needs to improve everything by at least 20% to be at the threshold, and to be below, to utilize this exponential downscaling of errors efficiently, one needs to improve even better. So conceptually, everything's there for quantum error correction. But in practice, one needs to improve, and improve quite a bit. And when this will happen and how this will happen, that is uncertain. So that leaves us with a question. There have been claims for quantum advantage, that quantum computers already perform something better than classical computers. How does it correspond to what I said? And the answer is twofold. One part of the answer is what were the problems and how exactly they achieved the advantage. The second answer, are we talking universal quantum computers, or are we talking non-universal computers that cannot run any algorithm? Instead, they can only solve specific problems. So let me talk about both. If we talk about universal quantum computers trying to achieve quantum supremacy, the earliest claim known to me is Google, again, 2019. They said they can simulate some sort of a weird probability distribution, and they can generate 1 million samples according to that probability distribution in 200 seconds, whereas the best supercomputer would take 10,000 years. It turned out that they didn't use the actually best method for classical computations in that problem. So people started doing estimate, 10,000 years became 5 days, and eventually they became 300 seconds by some Chinese team with a super powerful high-performance computer. It's not a laptop, but still, it's not 10,000 years. Then last year, Google published a paper saying that, you know, if we do use best algorithms and we're a bit generous with estimates, one can even simulate that thing in 6 seconds in principle. But if instead of 53 qubits and 53-bit probability distribution, we use 67, then it will take years even with that method. Could be, and they demonstrated the simulation here. So they claim they can still do it better, cannot be reasonably beaten by a classical computer. There is one more subtlety here. That's the accuracy of simulating that probability distribution. It's about 10 to the power minus 3. So basically what they simulate is a completely random distribution plus 10 to the minus 3 times a very specific distribution. Does it really solve the problem of simulating that distribution? I wouldn't say so. So formally, if you define the problem in a very narrow, specific way, say, okay, I'm fine with that, we have quantum advantage. Is it useful for anything, even for some academic purposes? I wouldn't say so. There was an attempt at a more useful quantum advantage by IBM last year. They said, this is our big 127 qubit quantum processor, and let's try to simulate some spin models, some discrete time dynamics of a spin model on this system. Why is this supposed to be hard? Well, this is supposed to be hard because if we have n qubits and spins, then the wave function is 2 to the power n complex numbers. And for 127 qubits, that's huge. If you want just to read each number once, it will take you an astronomical number of years, maybe even longer than the age of the universe. And storing that wave function, it takes an enormous amount of space. So you cannot simulate that with a wave function. There were, however, quite soon a few papers This is the latest of them, the most impressive one, where they simulated not only this 127 qubits, but also a similar problem on a bigger and even the biggest so far IBM quantum processor on a classical computer. And these are like 2 seconds, 8 seconds, 50 seconds, and even if infinite, its translation invariant, you can use some symmetries, less than a second per data point of simulation in that IBM paper. So that was an attempt of saying quantum computer can do something useful which cannot be done classically. Well, it turned out that this specific thing can very well be done classically. And it's instructive to think why it was possible to be done classically. The point is that you want a wave function, which is an exponentially big quantity, exponentially many complex numbers. But if you know something about your problem, you know that there is not too much entanglement in the problem, then you can approximate this wave function rather well with something called the tensor network. And if you approximate it with the tensor network, suddenly you need to think not of an exponential quantity of numbers, but only of a linear one. Okay, it has some extra polynomial costs to manipulate, still not exponential. That's what they used in this paper. And in general, why would quantum computers be better? The general idea, quantum computers can simulate something exponentially large, not possible to handle on a classical computer. That is correct if you want to simulate specifically that. But usually when there is a specific problem of interest, it has some structure. And out of that exponential amount of possibilities, you can select something much, much smaller, maybe polynomial, which is actually relevant for your problem. You don't need to simulate the whole Hilbert space. You can be fine with a small number, with a small part of it. There are other types of structures. There are structures related to so-called stabilizer states, other ones. So basically, quantum advantage is that you don't need to think about the structure of your problem. If quantum computers worked, you take any problem, you put it there, you solve it. But if you know the structure of your problem, turns out that classical computers are not that bad too. In principle, it should be possible to achieve quantum advantage over classical computations, but the structure makes it much simpler for classical computation. That idea is nicely reviewed in this paper called the Quantum House of Cards. The allusion is that quantum computer is like a house of cards. It's very fragile. It's very sensitive to all the imperfections. And we are currently in a state of a superposition. Will it work, or maybe it will collapse? So this is a beautiful review which outlines all the challenges on the way of building a quantum computer, from these gate accuracy, but also thermodynamic challenges that you need to do measurements for quantum error correction, and measurement requires resetting your qubits. Resetting is cooling, so you need to cool a huge system. So beautiful paper from a quantum computing skeptic, but the paper is written really nicely, really moderately, and really well argued. So it doesn't say quantum computers will never exist, but it shows the list of challenges to be overcome. So if you're looking for a problem, have a look. Now, up until now, I talked about universal quantum computer, a quantum computer that in principle could run any classical and any quantum algorithm possible. But there are also non-universal quantum computers out there. The most famous example is D-Wave. It's also based on superconducting qubits, but used differently, not to apply gates. What they do instead is they solve optimization problems of that form. And it turns out many problems can be mapped there. Just as an illustration, D-Wave exists since 1999. They started selling and providing access to their machines since 2015. So you see 16 years from the startup creation, company creation to product. That's an impressive amount of time. So how do they solve those problems? They can implement an Ising Hamiltonian on their qubits with transversal magnetic field and Z-oriented magnetic field. Z-oriented magnetic field is part of your problem, and transversal is necessary for the operation. It's not real magnetic field. I'm rewriting it in the Pauli basis for the qubits. These are superconducting qubits. So the idea is to use adiabatic theorem. You want to find a combination of binary variables that minimizes this cost function, so the ground state of the Hamiltonian. And the adiabatic theorem says that if you change things slowly and you start with the ground state, you always stay in the ground state. So if you initialize the system in a simple Hamiltonian to which you know the ground state, and evolve things slowly to the Hamiltonian which describes your target problem, you will be able to read out the answer to a target problem. And that's the idea. And this transversal field is needed to ensure that levels do not cross but anti-cross, so that you can really apply the adiabatic theorem. And there are always gaps between levels. That's the idea. Now they sell it. But does it actually work? Because, there is a lot of quantum hype. People may buy that machine or get access to use it just to say, look, we're using the most modern technology. We are advanced. Give us your money for our products. Or maybe it actually does bring an advantage. Turns out it does. So there is a use cases page on D-Wave. Some of them are dubious. For example, the free shuttles for some conference, how they should move around the road with real-time traffic information was simulated using D-Wave quantum computer and optimized in real time. Impressive? I'm not sure, I don't know. But I found one talk by a representative of a Canadian grocery company. Basically, they said that in around year 2000, they contacted D-Wave and they asked them to help with the logistics problem. They have 100-something stores. They need to understand how to send goods to different stores, when, and so on. And without D-Wave, the optimization was taking them 25 hours to solution. With D-Wave, it was taking 2 minutes. And it's an actual business case. They're happy, so the results are apparently good enough. You look at numbers, 25 hours to 2 minutes, it's 750-fold acceleration. So it actually does work in practice. Now, there are 2 caveats here. One is it may not be scalable. There are no theoretical guarantees for the scalability of this thing. Why? Because as you increase the system, there are exponentially many levels and the gaps become smaller and smaller. So you need to move slower and slower to be adiabatic, but you cannot move infinitely slowly because coherence time of your qubits. The other thing is, for the same reason, it's probably not the best solution, because there is decoherence, you make some errors. You are not perfectly slow, so you may get excited to higher levels, probably not too high. So chances are it's not the best solution. It's good enough, somewhere close to the optimum. At least the grocery company is happy. In a more academic setting, a few weeks ago, D-Wave published a paper. They used their machine to simulate a quench in spin glass. And again, they used these tensor network methods, and they say it cannot be done what they did with their machine. It cannot be done on a classical computer. It's supposed to be scalable because there is finite lattice connectivity. You simulate something. Why would there be problems? Now, what I could be skeptical about is tensor networks are a method for a particular structure. Maybe someone will find a different structure which is suitable for this problem, which would make it beatable classically. Still, if you don't want to spend time thinking, you can put your Ising Hamiltonian on that machine, simulate, and get some answers. So that's basically the end of my overview of quantum computing. Universal quantum computing needs to be improved, way to go to use the famous algorithms. Analog quantum computing, in fact, actually works. It may not be scalable in the sense of theoretical guarantees, in the sense of algorithm theory, but it does bring tangible benefits in practice. And now what I would like to do is to switch to what I'm doing in this area. I happen to be part of the French project for benchmarking quantum computing. Because as you have seen, you can claim quantum advantage, but someone should come and verify it. So it's nice to have a benchmark with a collection of problems. So for me, it's simulation of quantum physics models. There are other kinds of problems considered in the project. So with one type of code, one type of tests, which can be run on multiple quantum computers so that different hardware can be compared and one can say what works here and what doesn't work and what works there. That's the idea of the project, to develop those tests and make them available to the public and to the quantum computer companies so that everyone can use the same benchmarking tool to judge how things work. And what I'll use in my part in this project is, it actually started in a different thing. It was a German quantum computing project funded by the land of Baden-Württemberg. And they provided us access to IBM quantum computers and said, like, what can you do about it? So we decided, let's try to simulate the BCS model. Why the BCS model? One hand, it's interesting to simulate superconductivity with the aim of high TC superconductivity in the future. This is not, a microscopic model, but something related to superconductivity, real world, fermions, but it's exactly mappable to spins. So it's natural to simulate spins on a quantum computer, less so for fermions. So that's good. And it's also exactly solvable. It's integrable. So if we were able to simulate big models, we could ask some people doing Bethe ansatz to calculate how it works for big models and check that the quantum computer returns reasonable results. What turned out is that even simulating the BCS model with 3 spins, 3 Cooper pairs, 3 qubits, turned out to be quite challenging. So what did we do in this paper in the end? We took this BCS Hamiltonian with 3 qubits, so 3 spins in this language, which correspond in physics to 3 Cooper pairs, very modest, and try to simulate a quench. So we start with some state and apply this Hamiltonian evolution and see how it goes. First problem is that this Hamiltonian is not natively implementable on these machines. You see, D-wave, they claimed advantage on the Ising Hamiltonian, which is natively implementable on their machines. This is not. So what one needs to do is to break it down to trotter steps so that each trotter step is implementable on that machine.
Can you comment about quench? Because quench is not adiabatic. I thought that you can You can model on the
On D wave. That's their logic. But what we do here is we initialize some state. We do IBM is gate based. If I didn't make it clear, I'm switching back to gate based. IBM is gate based, so we can apply some gates, prepare some initial state, and then apply the gates which apply trotter steps, time evolution, according to parts of the Hamiltonian. And this actually is one full trotter step. You need to apply single qubit operations, and then in the BCS model, every Cooper pair interacts with every Cooper pair. So there are 2 qubit operations, and each qubit should interact with each one. So this is interaction of 1, then 1 interacts with 2, qubit 2 then interacts with qubit 3. Then you need to swap 3 and 2 so that 1 can interact with 3. That's the full thing. So you see, 1 trotter step under the Hamiltonian, it involves 9 noisy CNOT gates, which is quite a lot. But still, with 99.9% accuracy, you would say that this introduces about 1% error. Say it's not that good, it's 99, just 99%, 1% per CNOT gate error. Still, it's 10% error. You should be able to do up to 10 trotter steps. Now, we took the machine that was available to us back then, which was a rather old version. You see only 7 qubits, so it's an old one. And we tried to do the simulation, and this is what we should have gotten, and this is what we've got. Just nowhere near. It's horrible. It's a disaster. So then we dug the literature a little bit, and it turned out that to get reasonable results on modern day gate-based quantum computers, you need to use error mitigation. You need to run several calculations with which will allow you to quantify the error and extrapolate to what would happen if you had no error. That's one way of doing that, characterize noise and extrapolate results. Another way is the one which we used, is to say, if we know the model of the noise in our machine, then we could calculate something so that the noise would cancel and we would know the actual result. How it works, we used this error mitigation scheme. Imagine you have global depolarizing noise. So every time you apply a CNOT gate, you maybe keep your state or maybe reset it to a completely informationless mixed state. Then if you measure some traceless observable, then you can, then what you measure will be what you wanted to measure, the original expectation value of the observable, times exponential suppression with the number of CNOTs. But because this model is simple, it's exponential suppression. If you have 2 observables, you take the ratio, and the ratio of expectation values will be correct. So one can introduce noise estimation circuit, which is the same circuit as here. Just drop all the single qubit gates. And on one hand, this is the circuit with the same structure of CNOT gates. On the other hand, it's simple. 2 CNOT gates do nothing, 2 CNOT gates do nothing. This just swaps the qubits. So we know the answer of that circuit, the result of that. So we can measure the actual BCS simulation we're interested, noise estimation circuit, take the ratio, get a better estimate of the answer. That's the idea. Now, the problem is the noise, it does not have that simple structure. You think, I have a CNOT gate, and then I apply some noise. What kind of noise can I apply? Well, in general, this, and you see it has a tensor of coefficients for values for each index. 256 numbers characterize your noise. That's a lot. Okay, density matrix, it has nice properties. Trace equals to 1. Hermeticity, so it leaves you with 240 parameters, still a lot. But it turns out that if you are a bit clever, if you add some randomly chosen gates around your C0, if there is no noise, then C0 stays the same. But if there is noise, the noise changes, and the result is characterizable with 15 parameters only. It's called the Pauli noise. It's still not depolarizing noise, which would be if all of these coefficients were the same. And it's not global noise, which would be acting on everything as opposed to this acting locally. But we said we cannot do better. So we do this randomized compiling, and we use that error mitigation scheme and see what we get. So first of all, we did randomized compiling and see that the result did not change much, which is strange. Was the noise already Pauli noise back there? You could say so, because then randomized compiling wouldn't do anything, but it's inconsistent with these oscillations. Under Pauli noise, everything should decay. And here we have a revival. So it couldn't have been Pauli noise. What was it? Turned out to be crosstalk. So you apply a 2-qubit gate here, and you don't want it, but something happens to the neighbor, to the neighboring qubit. So we extended the randomized compiling procedure to simplify the noise structure also on the neighbor. And then you see the result did change. So we hit something correct, something reasonable. And then if we took these randomized compiling results and ran an error mitigation circuit and divided, you see, we get something reasonably close to what we expect. Not perfect, but reasonably close. And we repeated that for many observables. For some, it works nicely, like here. For some, it works horrible. For some, it captures the trend, but does not give the correct values. And in general, we averaged over all the errors. And this is the picture that we got. On the old machine, what we used initially, there are lots of errors, and about 60% of them are crosstalk. On the newer machine, 27 qubits, still not the newest, not the best machines, but one of the newer ones. Still a lot of error, and still about half of that is crosstalk. You apply a C0 gate here, and something happens to a neighboring qubit. So that's how it works. That's what happens if you try to do quantum simulation on a gate-based quantum computer. It's actually quite a lot of effort to recover some reasonable results on a rather small system, which you can simulate, I guess, in less than a second on your computer. But what I took from that is that this can be used for benchmarking, because this is application-based. This simulates a very specific physics model, which is integrable, so it can be verified. For small systems, you don't need integrability. You can just simulate it. But if we ever go to bigger systems, it can be verified. So it's an application potentially interesting to us. On the other hand, the way we explored this error mitigation structure, it allows one to tell what exactly goes wrong on this quantum computer and what should be improved. So that could be useful for quantum computer providers. And we'll use that as part of that bug project for benchmarking. One more remark is we wrote this in the IBM quantum computing language, Qiskit. If we want to run it on multiple quantum computers, we need some code which is executable on them without rewriting. That's a bit of a problem, but in this bug project, there is a company that developed a language called QLM. They called it QLM, Quantum Learning Machine. Now they've renamed it into Captiva. But basically, it's a Python library, just like Qiskit, where you can write quantum code, for example, like a code to create a Bell state. Looks like this. You apply a Hadamard gate and a CNOT gate. Rather simple. There is more beautiful computer science stuff in there, but I don't want to go into that. And they will provide us in the project with a paid version of their thing, which allows noisy quantum simulation, noisy emulation of quantum computers. So you take a supercomputer and say, what would a noisy quantum computer return? And they will provide us with the access to quantum hardware, but there is a nice byproduct, which could be useful not only within the project, but also for you, if you wish to try doing something. They have a free version, MyQLM, which you can install, which on your computer, use the same code. The advantage is that it's free. The disadvantage is it only allows gate-based programming, no analog, and only noiseless simulation. So you cannot simulate what happens on a noisy quantum computer with this free version. But still, it's a good thing to play with, and you can program whatever you wish. It has lots of examples in the documentation, and it has free conversion kits. So you can write everything in this language and then convert it to Qiskit or to Cirq, which is the Google quantum computer programming language, and to a few others, and there will be more eventually. So that's how we will solve the interoperability issue for running on different quantum computers. But also there is a free part of that thing, and you can use it if you wish. And that brings me to my conclusions. So once more, universal quantum computers have a long way to go before they become practically useful, gate-based quantum computers. But analog already have practical advantages, even if not advantages in the sense of algorithm theory. Now, universal ones, they have a long way to go, and on that way we need to benchmark them in an honest and transparent way to see whether we really are improving and how much. And this is the task of this bug project, and the intent is that the source code of those tests is published openly so that whoever wants can use it. That's it. Thank you for your attention.
Thank you, Kirill, for nice presentation, for nice talk, for many nice new things I learned. For instance, some question, do you have any?
Could you specify more what is the crosstalk?
Crosstalk is, I have a marker here. So the way people draw it is that this is qubit 1, this is qubit 2, this is, for example, qubit 3. I may have qubit 0, or I may have a qubit here and some neighbors. And imagine I apply something, some operation to a qubit. You would think, okay, I apply this operation here. Maybe I make an error. I want to rotate qubit by an angle pi, but I don't rotate it by that. I rotate it by pi plus or minus epsilon. That would be an error inside the gate, but to the neighbors, nothing happens. Now, crosstalk is that you apply a gate here and something happens there. Why is it so? Because these are physical systems and they have links connecting them. And you apply something here. How do they apply gate on a superconducting quantum computer? Well, they send some gigahertz frequency electromagnetic wave here, which drives the qubit and changes its state. They send it here, but through this link, it can link to the neighboring qubit. The idea is that the neighboring qubit has a different resonance frequency. So it should not do much, this wave to this other qubit. It's in a different spatial location, so the wave is weaker there, and it has a different resonance frequency, so it interacts less with the wave. Still, it has some effect. And since we are talking about, 99.9% accuracies, one starts caring about those effects. And so when I choose a subset of qubits, I do something to them, but inadvertently I do something to their neighbors that is called crosstalk. So this line is crosstalk.
Other questions?
Thank you for the very nice talk. I am interested in this thing of the thermodynamic cost of computation. And can you say something about that? So is there much difference between the different types of like universal or gate-based computation and analog quantum computation? Is there a big
Good
difference there?
question. Good question. I'm not a specialist, but I can say something because I talk to people. So in Grenoble, we have Robert Whitney, who is interested in thermodynamic cost of quantum computation. When it comes to quantum error correction, to universal quantum error corrected quantum computers, it can be huge. It can be huge because you need to measure. You mean to measure your errors, and quite often in the course of the calculations, you need a lot of measurement, a lot of resetting. Every time you reset, you pay something related to energy or entropy, and that will be a lot. Judging by what Rob tells, it can be for now the estimates is that they're trying to narrow down the estimates, but for now it can be anything from a typical high performance computer to a requirement of having a small nuclear plant next to the quantum computer, because that will be the amount of energy. They're trying to improve their estimates. So universal.
Is it because of the number of physical qubits that you need for the error correction?
Number of physical qubits that you need to measure them, that there are amplifiers, and as you try to denoise, you actually lose a lot of control signal. So a small part of your control signal gets there. The rest needs to be dissipated. I don't know the details. For that, I can connect you to Rob if you wish. So universal, it's not that optimistic. And in that review, Xavier lists that as one of the challenges. Now, for analog, for D-Wave, it's actually better, because D-Wave can solve some optimization problems not only faster, but you would use a high-performance computer that can, again, I have not checked the numbers myself. People told me that high-performance computers can consume up to megawatts of power, whereas D-Wave quantum computer, it consumes more or less what the fridge consumes to cool the system down, which is about 15-20 kilowatts of power. So analog quantum computer, for the problems it can solve, it already can give you a couple of orders of magnitude in energy efficiency for solving those problems. Now, the question is, of course, you need to keep it cold all the time. So do you find enough clients to load that machine with that all the time? But so yeah, universal thermodynamic cost is a challenge. Analog, compared to supercomputers, it can actually be good.
In other words, the big thing is the cooling, no?
Yes. In everything, the big thing is the cooling. The point is that if you do adiabatic calculation, you don't heat up much. If you do gate-based with gates and measurements and resettings, you heat up a lot.
Correlations between, yeah.
More questions? No questions? Let's thank our speaker again.
Thank you.